Good morning, everyone. Today is December 28th, 2019, and this is the John Chappell Natural Philosophy Science Chat. Well, I see today we've got quite a few people in the live room here. So I'm just going to add you to the stream here. So if you're not speaking, then just mute your microphone. And if you want to speak, well, you can raise your hand and get my attention. So let's see here. Is my headphones? Can you say something, James? Or yeah, somebody make sure my audio is working here.
Hello, good morning, everybody. Hi, Bob, Alistair, Ian, Phil, and Franklin.
Yeah, good morning, James. So have you been working on anything science related this week? You have any new projects you're working on?
I made a video on my vacuum composition work and paper, and I'm trying to make I'm thinking about making a video on navigating physics literature, because as I look up things on Wikipedia and other places, that publish information, usually at universities, about the current state of physics and knowledge in physics and so forth, I find that they're living in a fantasy land. For example, so I plan to do a video where we're just going to go through, say, Wikipedia and start clicking on things like elementary particles and so forth. And like for example, I was looking at magnetic monopoles, which are, by the way, the L-type bits. Everyone assumes a magnetic monopole must be a new or different type of particle, but actually it's a type of bit. And in binary mechanics, there are two types, the M-type and the L-type, which derive from the X and Y components of the complex amplitude. At any rate, the L-type bits appear to be, if not all of them, magnetic monopoles. But there's one thing, like they're saying, well, if there's a magnetic monopole, it's another kind of particle. Where I don't view the bit types M and L as particles. I view them as just binary energy quanta. Now, so I clicked
Although
on.
I've never really heard of monopoles as particles. That's a new one on me. You mean that that if the monopole existed, that it would have to be represented by a certain kind of particle? Is that what you're trying to say?
Well, yeah, like like when you divide up a bar magnet, for example, you know the two pieces that you divide up, are you're going to get a north and south pole in each of the two pieces. That's because the level of fineness is not down to the fundamental length constant L, where you can actually see the effects of north and south magnetic monopoles individually. And in fact, my paper on magnetic pulse injection into a randomized initial system state showed that by simply reversing whether you're going to have up pointing or down pointing L bits in the y-axis, you can move particles one way or the other. And I'm beginning to think that this experiment is even more important than what I may have thought, that it's actually showing the effects, at least in a simulation, of these L bits, which are apparently the magnetic monopoles. But again, I don't consider the individual bits to be particles. To finish up the thought on surviving physics literature, my tentative working title might be Physicist Survival Guide. I looked up elementary particles. Well, in Wikipedia, they have a nice feature where you can click on a linked item like, say, elementary particles, and up will pop the first sentence or so of the Wikipedia article on that subject. In other words, a very brief 1 or 2 sentence description of that item as to what it is. And it's very convenient to refresh one's memory in certain cases of what the terminology currently in use is. In the case of the elementary particles, they're saying that they show the usual standard model thing with the some 42 or whatever types of quarks, and these are elementary. And in their definition, they say these are particles defined as elementary because they cannot be broken down into smaller constituents, and so they're not composed of smaller constituents. And the interesting thing is that if you look at CERN papers, you'll see that some of these very heavy quarks, like the top and bottom quarks and so on, they openly talk about tracking the breakdown components of these particles. And so, in other words, as a survival guide to physicists, you have to realize, as Dr. Bill Lucas might say, actually, that what you see in the physical literature is they'll say one thing, and then elsewhere they'll say exactly the opposite. And
yeah, that's a good point. I think about they have the chart of, I don't know if they call them fundamental, but they call them the particles of
elementary.
the standard model.
The word elementary is used.
Perhaps elementary, because certainly they can't be fundamental. Because as you say, like, the Z boson, lasts for like a billionth of a second or something like that. And actually, they've never actually really seen one, but they've seen the decay products of what they think would have theoretically been one of those particles. And as Bill Lucas says, we've never been able to form a beam of those things. So I would say the reality of them is in question, right? You can't get something.
You put your finger on, Franklin, a very critical point, I think, that the decay time is so short. And what does the word decay means? It's breaking down into other smaller objects or particles. Could be photons, could be electrons or other fermions coming out, maybe some mesons or what have you. Now, by the way, I think the whole family of mesons is simply protons in motion, captured in motion. That you have. But I'm sorry, that's an aside. But so I think you did put your finger on it. So for the physicist survival guide, you see, Dirac. Well, I just thought I would go through and randomly click on things, and a lot of it is to help me refresh my memory as to what the actual definition of some of these terms is in physics, so that we're talking about the same thing when we talk to each other. But a lot of times I'm just shocked. Like they'll say the universal. I clicked on what's it called? The GUT, grand unification theory. Now here you have a case where supposedly the electromagnetic weak and strong forces all can be reduced down to a single force. But according to my work anyway, these folks don't have any idea of what a force is and how to mathematically define it. For example, there is no weak force, period. It's a result, all the weak interactions documented have to, are based upon the unconditional bit operation, which is not formally in binary mechanics classed as a force.
I'm not quite sure I would say that, but my analogy always been as like the weak force is like calling rust a force, right? You leave some metal out there and, it just, but that's like a chemical reaction. That's not a force,
Okay, well, at least we're agreed in the broad brush strokes there. So that's what I've been, maybe after today's session, I'll just click around because it's like a gold mine. You can click on any term and they'll say in physics, emergence or confinement or whatever is defined as such and such and such. And you say, and I say, really? I mean, this does not agree with the data. See, my work, everything in my work agrees with all known data, including the non-spherical proton shape, etc. So, and this is other people's data. It's not my own. So here we go with the quantization of space-time, and energy gives you a whole different view of what things are, and what's possible, what's not possible. And for example, in discussions here, people are talking about gravity fields, electromagnetic fields, and so forth. And I sit here asking myself, but what is there at X point in space? What is there? You must have some kind of a field decoding device. Well, if you're attempting to model all points because you haven't quantized space, that must mean that these field decoding devices are all infinitely small. For example, in Franklin's model, with he does quantize space into a cubic matrix, and has items which are to represent electrons and positrons and so on. But Franklin often, and others here, are often discussing, and of course there's the field. Well, as a physicist, I'm asking myself, well, what is that? And if you don't quantize space and time, by the way, too, if you don't quantize these things, you're looking at every single point, and that's the first thing they say in standard model mathematics. You know, they give the children's version of the standard model, and in Wikipedia there's another article called the mathematical model, the mathematical basis for it. And about 10, 15 years ago, I started to look at that, and it was a very short 3 or 4 pages of equations. Now it's about like 5 or 10 pages if you were to print it out of equations. And it's all based upon continuous space-time theory. And no wonder they have such a big problem, because they're trying to model something where there's an infinite number of points. That's the first thing they're going to say. The standard model mathematics attempts to model what's happening at all points in space. ALL, that's a literal quote, all points. Well, that's straight continuous space-time theory back from classical physics in the 20th century.
I was curious, James. So,
Yeah.
what do you think might be wrong about, like the theory that me and some other people are proposing, which is that space is just filled with a sea of positrons and electrons? There's at least 3 other people who are in that camp.
I would say, in my context, it's not necessarily to say you're wrong, because it could be I'm wrong too. Okay, but in you're up to the original Dirac equation pairing of opposite-handedness versions. In other words, two of the matrix equations, and that's where the positron was quote unquote discovered and later actually observed. What James Hughes did, which prompted my work actually, is he was a former MIT physics student, and during the 1970s and that upheaval period of Woodstock and all of that, he never finished his degree because he was out doing his LSD or whatever it is that he was doing. But at any rate, James Hughes rotated the matrices to show that they are actually equivalent to the 8 points of a cube. So in other words, it occurred to me that what James had done is basically say that what everyone was saying is occurring at one point in space. With real numbers, you can have 2.5 by 5, whatever, not integer number coordinates, but real number coordinates, which would include all points in space, to quote them. He was showing that it appeared that actually there are 8 different points neighboring each other, which form a cube, and that's why the relativistic Dirac-Spinner equation was so successful in predicting electron behavior, because it was taking into account the 4 other points, which I now call spots, as the 8 points of the cube that Hughes mathematically showed were mathematically equivalent. And when it comes to matrix algebra, simply rotating a matrix is about as simple as it gets, okay? So it's amazing that physicists haven't noticed this. At any rate, Hughes tried to promote his work and was laughed out of town in many cases at Princeton and so forth. But at any rate, the point I'm making is that so the electron and the positron are two of those points, and the 6 other points are quarks, d quarks specifically, and those are the elementary particles. And half of those 6 d quarks are matter and half are antimatter. So that when you have these 8, what I call elementary particles, you can show that every single quark, meson, and other particles that are positive, the Higgs boson, what have you, are all related to, are composed of combinations of d quarks and the 2 leptons, the positron and the electron. So in other words, it's sort of like these higher order or second and third generation particles, like the top and the bottom quark would be considered third generation. They're the heaviest and shortest duration, lifetime, and so forth, are actually compositions of these. But of course, if you click on elementary particles, they'll say, as I mentioned before, these are the ones that are called elementary. The criteria for that is that they're not composed of any smaller constituents, which is exactly the opposite of what binary mechanics is saying. So what we really need in binary mechanics, I mean, this can't be a 1 or 2 man show. We need actually dozens of physicists to be working on this. The magnetic monopoles, every single subject there, the speed of light, etc. All of these things. See, another thing, like you'll click on fundamental constants, and they'll say C, the speed of light, constant in vacuum. Well, my work shows it's not constant in vacuum, and in fact, a minimum quanta density is required to have any conduction of light at all. Period. So. In other words, everything you click on, you get a certain point of view, which is either irrational, illogical, inconsistent with the data. The only work that I know of, and help me out if any of you guys here know of another other information, is completely consistent with all data that I know about, including the LIGO experiments and so forth.
Well, you mentioned the quarks, so I have a little rant on quarks myself. Let me see, we're getting an echo here. That might be you. So I'm going to mute you there just temporarily, see if that helps it. So, but my little rant on quarks is, I think you got to be careful about when you accept all the available experimental data, that you accept things like quarks from the mainstream, because you may find yourself accepting something into your theory that may not actually be true. So I always have to be a little suspicious about theories which can accept everything, because that may just be that you're doing the same mainstream trick, which is to modify your theory in such a way to accept just about anything. I mean, if your theory is robust, there should be definitely areas where you can say, okay, I just can't explain that. That just doesn't work. But if you don't have any areas like that where there aren't any conflicts, then I would seriously consider whether you're fooling yourself, is be kind of my criticism there, if you can't accept everything. And but the thing about quarks, getting back to my little rant about quarks, because I seriously don't think that quarks exist. They've never been isolated. And in my discussions with people about quarks, they say quarks are necessary in order to explain, at least in a taxonomy kind of way, all the other observed particles and their decay patterns. So I said, no, you don't. You can explain all those decay patterns in terms of just positrons, electrons, because when things decay, they will decay into ultimately like electrons, positrons, neutrons, positrons. I mean, that's pretty much it. It eventually comes down to something that can be broken down into purely positrons and electrons. So why do you need quarks if everything that does decay eventually decays into positrons, electrons? So he challenged me. I think there's like a charmed quark or something like that, which is like this super heavy quark. now apparently when quarks decay, this charmed thing, the charmed sigma, I think they called it. When this thing decays, it gives off little baby quarks because it has, a quark made out of maybe 3 things, and then eventually it pops up that has got another 3 things, and something gets, and it just seems the decay chain, which you can follow, it just seems ridiculous to think that, this thing just spontaneously gives birth to additional quarks along the line. So what I did is I went and I looked at the decay chain and proved that at every step that can be recognized as a positron electron decay event. So to the point where, like, eventually, yeah, that thing decomposes into like 23 positrons and electrons. And that's also on top of the fact that maybe that charmed quark never actually ever existed, right? Because once again, no one's ever seen one of those things. You can't build a beam of it, but they just see this particular pattern in the accelerator data, suggesting that there was something there that decayed. I mean, the decay chain has got like at least 5 or 6 steps in it, and so they just see the end result in their in their accelerator and try to work their way backwards to get to this charm sigma thing. But there was really nothing that required either fractional charge or the up or the downness, or, and you've got at least a number of, I mean, if you accept quarks, you have to accept at least 6, maybe 9 particles, different kinds. There's up, down, there's colors. And all of that just seems to be suspicious, because it just seems that whenever they needed to explain something new, they just came up with another quark to explain it, right? And that just doesn't stop. And it's just not very satisfying as far as being simple to have, this half a dozen quarks, which, like I said, I seriously think they don't exist. And there was initially a lot of debate about whether it was just a handy mathematical nomenclature versus it being there. But I think nowadays the mainstream is pretty much, very much ingrained that these things actually exist, and we believe very ingrained that these things exist, having never actually isolated them, right? And then they have this very convenient explanation that, well, we can't find them because we can't find them, right? As soon as you try to separate them, you've added enough energy to make another particle, and therefore we'll never be able to see them, right? Well, isn't that convenient, right? Although I think there's been just a lot of experimental effort into actually either isolating the fractional charge or to actually isolate the quark themselves. And the net result of that being that, well, they've all failed. Me personally, I think they've done enough effort into this quark search to conclude that they don't exist, because I think they would have found it had they actually existed, or at least seen some more positive, direct evidence for something which is supposed to be so pervasive, yet they can't find it, right? All you find in the accelerator experiments is just wads of positrons and electrons. That's the primary thing that comes out of any collision of any particles. And that's they filter all that stuff out. That's like 99.9% of everything that comes out of these accelerator experiments, and their computers just automatically filter all of that stuff out. When I'm thinking, that's giving you your main result, which is that everything is made out of positrons and electrons, because that's what you see when you collide things together. What do you get? You get positrons and electrons. That's it, pretty much. So that's my little rant on why I hate quarks and why they're a complete lie, right? and if your theory actually includes them, then I would put your entire theory as suspect, based on the fact I don't believe there's experimental evidence for quarks. Let's see, you got to unmute you there, James. There you go.
Oh, thank you, sir. As we stumble along in the darkness, trying to figure things out, and yes, that's sort of what we're doing, if you will. One thing we can use is logic and consistency. So if it was such a great idea to use a pair of relativistic Dirac spinor equations to discover the positron, what about, and if Hughes is right, and his matrix math is really matrix algebra 101 actually, that these spinor matrices actually correspond to the points, the 8 points of a cube. Then we've got 2 of those points in the positron and the electron. So the question then arises, what are the other 6 points of the cube?
I would say that there aren't any. I mean, why make it more complicated? Why does he have 6 points?
Well, okay, you have the relative.
You could look at, to say, 6 faces of the cube, and that would be just as relevant, I suppose.
Well, for one thing, it's claimed, and I sort of believe it, that the relativistic Dirac equation was very, very successful, in predicting electron behavior. Okay, so that's one little handle that we have to hang our hat on. So when you combine a pair of these equations with opposite handedness, you get the discovery of the positron. And it turns out that if you rotate the spinor matrices in an appropriate way, you find that representation is exactly mathematically equivalent to the 8 points on the cube. So the question is what's in the other 6 points, the ones that are not the lepton points, okay? Now, I've tried to make my work a little bit user-friendly, if you will, by saying that that these 6 other points actually correspond to quarks, and the d quark specifically. Okay. Now, one confirmation of that is that I can show that all of the other quarks in the 3 generations of quarks, up, down, charmed and strange, and then in the 3rd generation, top and bottom, and so forth, both and the antiquarks that go with it are all, their properties, like their charge and their relative mass and so forth, are derivable from these 8 what I'm calling elementary particles, 2 leptons and 6 quarks. Half of these being antimatter and half being matter, as we categorize it. So there's a little bit of a confirmation that calling them quarks, but you see, my work in a way is, in fundamental terms, very more mathematical. In other words, look at the math, okay? And I caution people in various places that I try to, like, for example, the 2 kinds of quanta bits, M and L, I name might and light. The M bit being related to matter, having the charge property, and the light being related to maybe bosons or electromagnetic radiation, and so we're going to call it a light or an L bit. That's the origin of that. But I caution people to saying that this is just an analogy to maybe help people get into the story, because mathematically they're just 2 kinds of bits. Okay, M and L. Now, so now the thing that you leave out with regard to observing the quarks and their constituent products, such as the proton, is the fact that a lot of work by a whole lot of people who are, let's admit it, very smart, okay, think that hydrogen is a very important atom in the elementary table, and helium too, and that a whole lot of the universe is made up of this thing they call hydrogen, which is basically a proton with an electron wandering around somewhere, if we're going to talk about the hydrogen. atom as opposed to the hydrogen ion, which would just be the proton itself. So that when you say we can't see it, well, there's a whole lot of very smart people that think that, yes, there is such a thing called hydrogen. And in fact, if you're not careful with it in the laboratory, it's going to explode and blow you up. So that it's actually observable in there. Now, why we don't see the individual quarks? What I discovered by looking at putting a single bit in a non-lepton site in the spot cube, which is my model of space, okay? If you just put that single bit there in the simulation, you could have hundreds of thousands of bits in a simulation. What if you just had empty space, which I call absolute vacuum, to distinguish it from partial and perfect vacuums, which are in fact teeming with energy quanta, although everyone says they're empty space. So if you just put one bit there and follow it, start the simulator running, you find that after 21 simulator ticks, each simulator ticks is an application of the 4-bit operations, so that which are thought to occur in one tick each, or one time constant tick each. So that's 84 time constants of time passage. That bit returns to exactly where it was at the beginning. In other words, there's such a thing as the proton bit cycle. The same thing for the electron, but in that case, it's only 3 simulator tick, where a single bit put in an electron spot will return exactly to where it was at the beginning. So you've got these bit cycles. Incoming quanta will tend to be captured by these cycles, by the way, because once the bit enters one of these bit cycles, once a quanta enters one of these bit cycles, it will tend to cycle there for forever and ever until some very specific things happen, which allow it to exit the cycle. And whenever a quanta exits one bit cycle, by definition, it's entering another, which is the basis for all particle motion. Now, why, getting back to Franklin, why we don't see the quanta? This is called color confinement, okay? And the discovery, and I have to call it that because I was just following my nose. I mean, don't give me any credit. I just wrote a little program, okay? And I found, my God, if you do that simple experiment in the simulation, the bit returns after a certain number of simulator ticks, which is 21 of them, to exactly where it started. That's the cycle. By the way, in the original 2010 paper, written 16 years prior to that, actually, but published in 2010, this what I called then the baryon cycle, the central baryon cycle, was defined based upon the postulates of binary mechanics. You know that there are m bits and l bits. What is the magnetic potential? What is the electric potential, and so forth. So at any rate, that's your problem in seeing the individual quanta. It could merely be a problem of the individual quarks, I should say, pardon me, that they're captured in the bit cycles, and we catch them in transition, probably as mesons, when a proton is moving from one location to another. And that's what I can say in response to that. So when you say there's no evidence for quarks, you can ask yourself, what is the consistent picture here? First, the Dirac relativistic Dirac spinor equation, just considering electrons and positrons, was magnificent in predicting electron behavior. I mean, there's nothing better than it as far as I know, as a matter of fact. Now, then you have the fact that Hughes comes along, James Hughes, the former MIT student, coming along and doing his little matrix algebra thing, which he showed me on a blackboard in my kitchen back when. And I said, gee, that looks like regular garden variety matrix algebra to me. It looks okay. I used to write computer programs for factor analysis, canonical analysis. It's all matrix algebra, folks, inverting matrices, all this stuff. At any rate, what Hughes is just a simple rotation. Okay, I mean it's like, as I said, matrix algebra 101. At any rate, so you have that. You have the presence of hydrogen and these atoms in the universe. You have nuclear physics that talks about that there are these things called nuclei. Now, if you have, Franklin or anyone else, a better idea as to what these nuclei are composed of and how to study them and to analyze them, I'd love to hear it.
Certainly, that's an area of my interest. But I mean, just to contrast the varying methods, it's like you can try to explain things, say, mathematically, as you say, on a board, and you can try and simulate certain things. That's certainly one way to go about it. That would be in contrast, because I'm more of a materialist kind of person. So you show me a blackboard full of equations, that might as well be written in Greek, which it in fact is. And I just, you can criticize me that I don't really understand how all those equations work. And to a large extent, I would say that I don't care that they work either. Because as a materialist, I like to, play with things, things like billiard balls and such. So my approach would be, instead of looking at the blackboard, for example, you mentioned the discovery of the positron by Dirac, but I don't think that the equations discovered or really had anything to do, because the positron was just there all the time, right? It's not like Dirac had to have his equations make the positron in any way.
Well, the equations, if I may interrupt, the equations are part of our little effort to understand the reality in which we are embedded, by the way. Okay. So the binary mechanical space time energy frame, we're embedded in that. And so you say, well, we forget,
or it might not be. It's kind of thing that the thing is, in order to support that, you need to have an experiment to say that thing actually exists.
Yeah. So
and I'm not sure that
or does not exist.
Well, the thing is that,
where is your experiment, Franklin? Where is your simulation of your model, where you can create a hydrogen nucleus? In other words, a proton ion, a hydrogen ion, excuse me. And
well, I think because I don't have any.
We love to look at it, but simply to say that it's as if you're saying, if I were to do this, then I think that maybe my point of view would be verified. So you can state your point of view, yes, and maybe someone else will pick up the story and show that what you're saying holds water. But for the rest of us, we have to just crawl along the floor, so to speak, looking for any logical consistency we can. And as far as I know, everything in binary mechanics, with the quantization of space-time and energy, is self-consistent.
Yeah, so we realize that self-consistency is, of course, I think we discussed this in the other science thing, is that self-consistency is kind of like the very basic level that you have to come to. But certainly self-consistency is not any level of proof that your theory is correct. I mean, it's good that it's self-consistent. It would be bad if it's not consistent.
Well, this is more the philosophy of science than science itself. I take this comment to say, well, one of the criteria that we use is logical consistency. You say, well, but that may or may not be totally important. Well, there's a number of criteria that we use, and but just simply to say, you have to offer something. So
yeah, well, I would say that everybody's theory is probably self-consistent, and we obviously all can't be right. In fact, probably we're all kind of wrong.
No,
but,
I don't.
Let's see here. Now, I need to go and take care of my mom.
Everyone's theory is not self-consistent.
I want Ian to jump in here while I go find out what my mom wants. Okay.
Okay.
So, Ian, what do you think?
Take care of your mom.
Okay, well, I've kept quiet up to now. I'm quite enthralled listening to you two gentlemen. I mean, I think I have an open mind on the subject, and I'm listening to the various points. I often think, though, is there any logical termination to our splitting up the atom, into smaller fragments? I mean, the original Democritus idea, I suppose, is you have an unsplittable element which makes up all matter. So that's the atom, not splittable, atomus. And then you do further experiments, and you say, well, look, it must be made. Rutherford's experiments and so on, it must be made up of a central core, and then you look at electrons, and you look at protons, and you look at neutrons, and then as you say, you look at positrons, the converse of the electron, and then further on you look at quarks, which are the subject of your debate at the moment. This sort of splitting up of the charge of the fundamental electronic charge, into thirds or 2/3. Now, maybe that itself should be split up into, or could be split up into smaller elemental entities of charge or particle. I don't know. I mean, the process maybe is a little suspect in that we're just doing more and more experiments, and then we're saying, oh, well, you've got to split that up again because the experiments indicate that perhaps it's not an integral unit in itself. It's not an elemental unit in itself. So maybe logically this process might never stop. It's the swifts. Big fleas have little fleas upon their backs to bite them, and little fleas have lesser fleas, and so ad infinitum. Keep on splitting. So I'm just wondering, could one establish that even if one established that quarks were the elemental charge basics, is there any reason to believe that we should stop there?
Well, in my work, as some of you may recall from my previous presentations, each what I'm calling the 8 elementary particles, the 8 and only 8 elementary particles, are each composed of 3 items which I call spot units. The spot units are 2 adjacent L-sized cubes, which can contain an M bit and an L bit in either the 1 or the 0 state, so that you have up to 6 quanta in each of these elementary particles. Now, I did some further work to say, to ask the question, what machinery, you might say, must these spot units have in order to implement the fundamental bit operations? By the way, someone asked last week about the differential equations. Now, the time development infinitesimal differential equations used in quantum mechanics are inapplicable because time is quantized. So there's not infinitesimal increments in anything. There's binary increments and things. So I just wanted to throw that in with reference to what happens with the differential equations question from last week. But getting back to the quarks, then each one is composed, each one of the 8 elementary particles, including quarks and leptons. And by the way, I'm calling them quarks because it looks like the collision work that people have done with particle accelerators. There's some smart cookies doing this. They decided to call this the d quark and the electron and the positron and so forth. So I tried to use the same terminology, but you can look at them as just labels if you want for these 8 elementary particles. Now, getting down to the breaking things down, I found that the elementary particles really aren't the elementary building blocks of the universe. In fact, analyzing what mechanisms a spot unit must have to implement the 4 bit operations, which are the time development or time evolution laws of binary mechanics, I found that there's only 4 kinds of spot units. Whoopsie. This means that we reduced 8 elementary particles down to 4 kinds of spot units. And each spot unit, of course, has 2 bits, the M and the L bit. So that you see that even in my work, I'm finding that the elementary particles are not as elementary as people thought, but rather the basic building blocks of the universe appear to be spot units. Now, you might say, gee whiz, as I look out into the night sky and stars so far away and so forth, this must involve an incredible number of spot units to form spot cubes and so forth. But if you look at this is easy as pie to build compared to, let's say, string theory, where you have vibrating springs. And what is vibrating strings? This goes way back to classical physics, where you're going to have real numbers again. Nothing is quantized. It's all you're going to have a supercomputer at every single point. And since there's an infinite number of points in any volume, these supercomputers to calculate all this, if string theory and other theories like it are to hold any water or logical consistency, would have to be, these supercomputers would have to be infinitely small. In other words, when Franklin is saying that logical consistency, that anybody can invent logical consistency, apparently the physics community and the powers that be therein have been unable to make their own theories, which are published and widely disseminated in textbooks, logically consistent. So that because the minute you want to model all points, at that instant, mathematically, you are saying that whatever physical events occur at any particular point must be infinitely small. Well, in elementary school geometry, and I still recall this, a point is like nothing. It's just a coordinate in space. There's nothing there. It has no dimension, no length, no height, width, depth. It's nothing. So basically, if you want to look at whether a lot of the current theory, for example, the standard model mathematics, I mean, I'm not saying throw it away. At a more macroscopic level, the binary quantum effects that I'm talking about will average out, and so therefore you can use Maxwell equations to build big magnets and things like that. But so in terms of building useful devices, they're really handy. Shooting rockets into space, I think somebody was saying we're still using Newtonian physics for that. At any rate, there is logical. So I take exception to the argument, oh, anybody can just make what they're saying logically consistent. Show me. The physics community hasn't been able to do it.
Yes, I'm quite interested in Jim, your statement and your work. I think you said earlier about the inconsistency of modern physics, and this has struck me as well. I mean, one could, in many respects, accuse them of a sort of an Orwellian double speak. You know, they say one thing when it suits them, and then they say another thing when it doesn't suit them. They sort of like talk about GPS as being the arch example of the being consistent with relativity. And then when you look at the sort of Sagnac correction or something, which is the converse of that, they say, oh well, that you're looking at the wrong thing. It's a non-inertial system, and therefore it is consistent, where it's actually quite the converse. So that's quite so. I'd like to ask actually in a moment. Are there any other views from people like maybe Bob or Alistair on this? But just maybe one or two things. One thing just before I leave the subject is, your statement, Jim, about continuous versus discrete and so on, which is interesting, and maybe the use of the calculus in describing events in the world, but one can go further, and I suppose that I'm being really the arch skeptic now in this statement. I can say are any of our theories, whether they're logically coherent or not, are they ultimately true? I mean, perhaps they're just models which work. Work in the real world to a certain extent, but do they really represent what's going on in the real world? So that's a sort of a philosophical point. Mm-hmm. By the way, just before getting back to handing it over back to Franklin, I'll just mention something very briefly, if I may. There has been some correspondence, which some of you may have seen, from Akinbo Ojo. He was watching the proceedings last week, and he just wrote to me, and I think he copied it to a lot of other people, just saying that he'd like to tease out some of those matters a bit further, perhaps by email. So I suggested we might do it by one of these conferences, but he said that he finds it difficult in his environment to speak because it's very noisy or something, but he can listen, or he can certainly listen to the recordings. So I think he's going to listen to today's recordings and maybe send me some emails. But I apologize to him maybe on the air now, because we're not covering that subject, which is fair enough. I mean, we did go into quite a bit of detail last week about that. Incidentally, he lives in an area in Nigeria on the Gulf of Guinea, which is not very far from where the Principe experiment was done. So that's one thing. But I'm just wondering, Franklin, if anybody has any further views on the subject, Carl, Bob, or Alistair. By the way, Carl Reith, who's here, I just see Carl Reith and Cornelius wrote to me saying they'd be interested in carrying on that conversation a bit further on the gravitational bending of light.
Yeah, so I invite anyone else who is in the live room, Carl or Bob or Alistair, to comment. And generally speaking, so we did have a few more people in the live room than I could put up, but now we have 6, so that's fine. But if you would like to speak, go to our live.naturalphilosophy.org, or if you would like, but otherwise, if you just want to listen in and you don't want to speak, then you can just go to like youtube.naturalphilosophy.org, and you can just listen there. Otherwise, I'll presume that you do want to speak, and I may call on you at any time. So, like, I'll call on Bob. Bob, we haven't heard from you today.
Good morning, my time anyway. Well, I don't know. I'd like to understand James' model much better. In fact, I don't understand it at all. But it sounds quite intriguing. One comment, though, from what I know of the Dirac equation when I was a graduate student working with that stuff, I kind of, that's very mathematical. And so when you say that someone takes a, I don't know, SU2 rotation matrix or O3 rotation matrix and comes up with other points for a total of 8 that may make a cube. To me, that sounds very much like just a normal symmetry argument, that the equations appear to have a certain amount of symmetry. Okay, so there's 8 symmetry operations, or there's 8 symmetry aspects to the equations. I don't see that being translated necessarily into a physical 8 corners of a cube. I see it more as as they say, a mathematical representation of something, and it's the physical something that I don't think we'll ever know. But it may be that we don't need to know what it actually is if the mathematics is sufficient to describe it and to provide us with the ability to predict either other particles or other dynamics or other physical phenomena. And then, of course, you can get into a philosophical discussion. Well, if it completely describes it, it being reality, then why isn't that actually it? So I'm kind of on the fence of, and I kind of like to think, although I'm talking, I know nothing really about James' theory, but I have in my mind that what he's talking about is a mathematical symmetry and not necessarily a physical thing. And it's just amazing that with that kind of symmetry approach, he can develop so much, as he says, all of the fundamental constants and the particles and etc.
Well, the whether or not things are real or we're living in, we ourselves are part of a big simulation is beyond my pay grade to answer. We'll have to let the philosophers deal with that. To respond to Ian's message, my work just starts with what happens if you quantize space, time, and energy. Once James Hughes showed this 8 points of a cube being involved in the spinor matrices of a pair of relativistic Dirac equations of opposite handedness, I took it from there and said, well, what if we just quantize everything? Time, space, length, and so forth, and made that as our fundamental postulate. What are the consequences of that? And I more or less just followed my nose. As I said, even in the original paper, I did define what looked like to be what I call the central baryon bit cycle. Bit being a one-state bit, or what I'm calling an energy quanta to make it more user-friendly to other scientists, you might say. But it led to the discovery, once I developed my simulation program more, of what I'm now calling the proton or hadron bit cycle. And by the way, there are 42 locations in bit loci in this cycle. So that means there are 2 to 42 to raised to the 42nd power number of possible hadron configurations, just considering only one spot cube. All right. So this seemed to be able to take into account really all of the complexity. So to get into my work, just start with space-time energy quantization and ask yourself, what happens when you do that? What happens is you discover the proton bit cycle. You discover that a logical explanation for matter, antimatter asymmetry, which some of the foolish people say must have happened way back in the Big Bang era at some point. You discover all sorts of things, which are the asymmetrical proton shape, the zero electron, the zero electric dipole moment of the electron. It just goes on and on. So that that's the way to get into it. As I say, I'm producing more and more videos on my BitChute Binary Mechanics Lab channel and the papers and so forth. But just it's amazingly simple. The mathematics in the actual bit operations require one logical function only, the AND function.
Yeah, James, you've been very prolific in that respect. So, Bob, he's got plenty of, you could probably spend days in his website and watching his videos. Lots of stuff to support what he's talking about there.
Great.
But James asked, what are your experiments? Which I think is very important. So, like we said, the first level is, logical consistency. Another level is, what experiments are there to support your primary fundamental ideas of your theory. So, in James's theory, he would have to prove the existence of basically his bit spot, right? That's the basic thing that everything revolves around, which would be kind of hard because it actually exists at a different level than what we can physically observe. So I would see that would be kind of hard to experimentally prove that there's this underlying thing, because experimentally we only see things like electrons and protons and neutrons. If the electron is in fact an aspect of some other exterior mechanism, I'm not sure how you experimentally go about proving that. Theoretically, it might be impossible. The only way you can do is kind of confirm that if you had such external features that it would generate the visible particles that we see. But once again, that's still be a self-consistency problem. But James challenged me to okay, what experiments would I have to support, say, my hypothesis, which is that space is filled with positron electron sea, essentially, of some sort. So if that's true, space probably looks something like this, where the red bricks are like the positrons and the red and the black blocks are like electrons, and so they would probably be in some kind of checkerboard matrix so that they don't repel each other or something. So what would be the evidence of that? That would be that if this existed, then theoretically I should be able to break this apart. Eventually I should be able to get separate positrons and electrons, right? So that would be one experimental evidence that if space is filled with these things, then I should be able to look at a completely blank piece of space, should be able to shoot energy into that and get out positrons and electrons in exact pairs, right? You should never get out two positrons. You should never get out
Franklin,
one electron.
What is the energy you're
confused.
shooting in?
The energy is what happens to correspond to what is E equals mc squared. If you put that much energy into a bond, and this is actually what we do observe. We do observe in pair production that if you put in what is effectively what we think the binding energy of this thing would be, and it's the same energy you get that when these two things come together, they release that amount of energy. It's a chemistry analogy. In chemistry, when you react hydrogen and oxygen, it releases energy. That's the binding energy. And in order to split up the hydrogen and the oxygen, you have to put in energy, and you get out the individual hydrogen and the oxygen. So if I'm just saying that experimentally, if space were filled with a positron-electron matrix, then we should be able to observe splitting apart space into individual positrons and electrons. And we actually do observe that. That's known as pair production. We should also observe the emission of energy back into the bound state, which would be the positron and electron. And we, in fact, observe that as well.
So what is the energy? You just say E equals
the energy is E equals the amount of energy released on the collision of a positron with an electron is equal to the kinetic energy of their collision, which is 1/2 mv squared plus 1/2 mv squared. The maximum speed of these particles.
Basis for it.
No, there is. The maximum speed that these particles can travel through natural space is the speed of light, c. So if you add 1/2 mc squared plus 1/2 mc squared, the energy you would expect from these two collisions if this is if all the kinetic energy is released as an inelastic collision, would be mc squared. And that's exactly what we observe. So there is totally a physical basis for why why space should consist of charges. I mean, it seems,
Franklin,
it seems that
I don't understand. I don't understand what you're doing when you're holding up the cubes and you're saying this is all space, and now you're splitting them apart, but now you got a space in between your cubes, but that space has to be filled with all cubes because you say space is all cubes, so you can never separate a cube from another cube because that requires a space without any cubes in it. But you say no, everything is a cube. I don't
everything
understand.
technically has to be at least a dipole pair, because the only time you can recognize a separate electron is if it's by itself. See, as soon as you put it together with its mating positive charge, it disappears. So the only way we can recognize it is if it's here. So, but you can have this separated, like once.
But what's
you can imagine space being filled with these things. The space is going to be filled with these dipoles all the way around.
Right.
But there's going to be an unmatched charge in here. That's the thing we can see. When you're matched up, you can do that. But when you split this thing, these things will go in between, the individual. Like if you got this, oops. If you've got positive and you've got negative, they were put together, but as soon as you split them up, another one of these guys is going to come in between, and this has to get far enough away from that in order for you to actually recognize that this is now an electron and this is now a positron. So I would say physically and experimentally, that's what we're talking about here. What experiments support your hypothesis? So I'm just saying that that very basic basis, that space is filled with positrons, electrons, is satisfied by the experimental evidence, in that we do see that you can eject positrons and electrons out of what is arguably, vacuum space, right? So I'm saying there is no vacuum space. Space is filled with positrons and electrons. So you should be able to separate them out, and we can, right? So that is something that actually all models need to be able to explain. Why is it we can do that? And the other curious thing is, why is it that it actually has to be in the presence of, say, a large atom? Because you can send gamma rays through space as high energy as you want, and it will not split apart space. It has to be kind of in the region of some gigantic atom. And I would say that that's probably due to the fact that it's an inertial argument, and that if you send a wave through particles made out of this stuff, it can go as fast as it can. It can go absolutely as fast as it can. You can put as much energy you want and will not break it apart. But if it actually physically runs into something very large, then it cannot respond instantaneously, and then that will cause the particle to break apart at that point, and only at that point. That's another thing we have to be able to experimentally explain. That's another experimental result that we have to be able to take.
So James, in your model, would you say that all of space is a cubic lattice, and what you're describing are patterns of something that goes around the edges of each of the cubes to form cycles, and it's the pattern of the cycle which you're identifying with a particle, but you're not splitting out a particular cube out of that lattice or anything? So
you could say that because Franklin has his blocks. Here is I put this together to help myself visualize the spatial model. This is tricking the camera because everything is reversed. But here we have, for example, the electron. Let's see if I can get this oriented to where there, the yellow, and then how do I have to? There we go. Here are the 3 spot units of the electron in yellow here. And if we just flip the cube around to the other side, we have the positron here, which is on the solid diagonal. Let's see how it rotated to show you the positron. Well, I'm wasting time here. There, the positron is on the solid diagonal opposite from the electron. And then we are going to have 6 other assemblies of spot units. And so basically everything in physics in my spatial model is based upon the existence of quanta, energy. I'm calling them energy quanta. Mathematically, they're one-state bits, bit loci, which are in the one state. So when Franklin says we shoot energy in, I don't have to add anything in my model. A laser beam, whatever it is made up of these quanta. There's nothing else but these quanta. So that you might say that the basic, once you quantize space-time in energy, the smallest unit that we now know would be, in my work, is the energy quanta, the one-state bit. And that can't be divided any more than that, as far as is known at present. Now, part of the prison that conventional physicists find themselves in, from the textbooks and so forth that they use and the lectures that they give each other, is that many of these physicists have spent their entire life using differential equations, such as the Schrodinger equation and the Dirac equation and so forth in quantum theory, to and work with these equations for their entire life. And so the minute you say, I'm sorry, there is no infinitesimal increment in time, you're going to have to quantize that. It means that basically all of their work is thrown out the window. So can you expect them to say, oh, well, wonderful, thanks, we appreciate you letting us know that? No, they're going to be even violently opposed, or at least violence up to the point of censoring binary mechanics. Okay, you got lost at quantized time. Well, let's say you've got a differential time development equation where time can have infinitesimal increments. If time is quantized, it means there can only be binary increments in time. Time is measured in integers now, not in real numbers. And
Although somehow I used to think that he's got some experiment to refute it. So you can't refute experiments with equations. Of course, I don't know what experiment he's done.
I'm not refuting any experiments. All the experiments that I know of are consistent with binary mechanics. And in fact, one nice thing about binary mechanics is its incredible predictive power compared to, say, string theory, where people say, but where are the predictions? And people are desperate to come up with one or another predictions that can be experimentally tested. All of the predictions of binary mechanics are confirmed, and for the most part, by other labs.
But he's saying that he has an experiment that refutes quantization, I suppose. Now, that could be an experiment that you don't know about, or could be he could be interpreting that the way he likes, I suppose. Unfortunately, he doesn't have it. I don't think he's here to particularly comment on that, but we do have this other comment here from Jonathan. Equations work. And certainly, I mean, that is one of the things that physics do, is that we take the empirical results, we fit them to equations, and then they hopefully help us predict the results of other experiments. Although those equations and even those empirical results don't really tell us the mechanism behind them, right? Like if I say kinetic energy is 1/2 mv squared, that gives me the right answer every time. but really doesn't give me any intuition as to why that is. Why is it 1/2? Why is it not 3/4? Why is it not 2? Why is it M and why is it V?
Well, another thing that imprisons physicists is precisely these constants, like the speed of light, Planck's constant, electron intrinsic dipole moment, electric dipole moment, I should say, and magnetic moment as well, elementary charge and so forth. When physicists find out that their entire work has been based upon a body of unexplained observations, and that's what these constants are, the speed of light, the ones I just mentioned, they are all a body of unexplained data. And when they find suddenly there is what I call the leading theory in physics today, can derive these from just a little handful of fundamental postulates. People just throw up their arms. As a matter of fact, I was talking to one physicist in a social media site, and he was saying, wow, this is interesting. This is really interesting, because nobody has derived these fundamental. There's no theory in physics that has derived them, and look at what you've done there. And then as the conversation proceeded, he then moved the goalpost. He said, well, not only do you have to derive all the fundamental constants to show that binary mechanics has some degree of credibility, but you have to explain every other thing in physics that is at present unexplainable. Well, that's ridiculous. That's not the way science progresses. We go a little inch at a time, and we work our way closer and closer to what might be the most realistic view of things. Now, I was asked at the onset what my recent work is. Basically, it's now down to the spot unit being the most basic building block of the universe, and even below that are parts of the spot unit that are required in order for the time development laws of binary mechanics, which are simply a quantization of the Dirac equation, including electromagnetic fields. Okay, so you get that in there too. And you get to things like bit sensors, and these are almost two-dimensional. I'm not saying that they're exactly two-dimensional. There could be a third dimension, but they amount to like a side of one of the bit loci in a spot unit. And a bit sensors would be required to know if there is a potential in the adjacent, a potential being another one-state bit, in the adjacent bit locus. So you need bit sensors, or quanta sensors. And then also, what about the direction of movement of quanta from one locus to another? It's not arbitrary. There's only certain ways they can go, or directions that they can move in. So you're going to need something called, again, a sort of a two-dimensional object or a side of a bit locus that we're going to call a bit valve, okay? Which will allow a one-state bit to go in one direction from one cube to another, but not backwards. A bit valve, much like fluid dynamics, it might have a one-way valve, or the heart has one-way valves in them. So there are just two. And so what we need is some smart people to start looking at this. This is the cutting edge frontier in physics today, okay? What else? One could actually say, I'm going to get here's a spot unit. If I can get my finger to the right place, not there, here. Okay, see, there's a spot unit. Here's the M bit, and by triangles is the L bit. Okay, so there's just one in a blue that would be a matter D quark. Now, what else do you need? One could actually build a physical model of the time development laws using levers, ratchets, springs, whatever, to actually show the the time development laws of binary mechanics. And so far, every experiment I've done using these laws gives me results which are consistent with known physics. Okay, so after a while, you start to say, well, gee, this must be a complete list of the time development laws in binary form. This is why they're called bit operations, and that's where your differential equations went. So again, the part so we mentioned all the math work involving continuous space-time theory era, which is ending now, and all the major achievements in physics, advances in physics knowledge, have occurred from the classical physics on through relativity on up to the standard model. That era is now ending. And we're in the process, in my opinion, of a regime change to the binary mechanics era, or what we might call full quantum mechanics. It's ironic that quantum theory folks resist, apparently, the idea of full quantization, and those are quantizing space, time, and energy. And this is one of the barriers that they have. They spent their whole life in the continuous space-time theory era, and they can't even think outside that box. So right now, I view part of my mission, at least on the public relations side, to try to convince and recruit people who have some knowledge about physics and want to do research to help carry this story on. Because
I think they did call it, quantum physics. So I'm not sure that your assertion that everyone thinks things are continuous would be, I don't know. If you said that to a mainstream,
that's why I call it full. It's partial quantization. Quantum physics is partial quantization. Binary mechanics is full quantization. It's that quantum theory that Franklin just mentioned is incomplete quantum theory. Full quantization is complete quantum theory. It's
then
sort
can you
of like
explain,
growing up from adolescence to adulthood.
Well, can you explain this specific experimental result, which is kind of the basis of why they said it was quantum, which is the quantized spectrum. So when you excite a hydrogen atom, the wavelengths that come out of it, which are quantized, right? I think that was probably the quantum of quantum physics that started it all. So, but I was wondering, does your theory have a specific explanation for that?
Or yeah.
So what is it?
In the binary mechanics lab simulator, you can the output files record the number of quanta leaving the simulated space over time. You can do a Fourier analysis of that and get all kinds of spectrums.
But do you get the spectrum which is observed, which is for hydrogen, you only get like 4 visible lines plus a bunch of other lines.
I've got megabytes of data which I haven't even analyzed yet. If you download the hotspot.zip file, which contains all the software I've written so far, there is a frequency analysis program there, which seems to show various peaks, and which would be your spectrum that you're talking about, and also a large what do you call it? Black body type of radiation curve. Okay, and so all this needs to be analyzed. There's only so much one guy can do.
Well, that's kind of like the most fundamental thing you could analyze, which is the spectral
result. So you're
result.
going to do it. Great, fantastic.
No, I mean I would do it for myself. Because I think your system is far too complex. If it's producing that many numbers, the spectra runs with the Balmer formula, which is very similar, very simple formula. In fact, it's like 1 over R minus 1 over R2, basically. I mean, it's just that's it. Now your theory needs to account for that? I mean, you're saying that binary mechanics accounts for all of the data. So I just handed you an experiment which would seem to be fairly simple, and you're not giving me a straightforward answer. You're saying, "Oh, go look it up yourself."
I'm giving you an exact straightforward answer. Let's not try to make things
No, a straightforward answer would
unclear.
be yes.
My straightforward
I've
answer
predicted-
is I haven't done that experiment yet. But you
well,
could.
then you
Because all
haven't.
you
Then
gotta do
there
is
could be an
download
experiment that it
my
doesn't match with.
software and run it and look at where the emission lines are. One
Well, I
major
would
emission
suggest
line.
that you do it. Oh, Jonathan Erickson Spot says he'll give it a try. You can recruit him. There you go.
Well, you see, as they say out in farmland, there's only so many. There's only so many tits for the little piggies. Oh, okay. At some point, the little piggies have to step up and do something, rather
this is
than
not a
expect
small
everything
thing.
be served to them on a spoon.
This is not a small thing. The predicting the spectra. I mean, also it's like, how do you explain pair production? Do you have an explanation for that and why it occurs the way it does?
Sure.
So what is your explanation for pair production? That's just another experiment that we all have to account for.
The quanta arrive, incoming quanta arrive in such a manner that a pair is produced.
But that's not, all you're saying is you're just repeating the observed result. That's not really an explanation for why is it always a positron and an electron pair. Why is it not two positron pairs? I think that would be perfectly possible.
Okay,
in your
here is
model.
the explanation. If you can reproduce that with the with the spatial model and the time development operations of binary mechanics, you've increased the credibility of both of those as a scientific theory. If you can't, you've shown maybe some defect in it. The same way for the frequency spectrums that you spoke of. If you can reproduce those with the spatial model and the time development laws of binary mechanics, and that's what quantum theory is all about. You have, what is the thing that you have? That's the spatial model with 1 and 0 state bits. That's your system state. The other thing in quantum theory is how that develops over time. If what I have enshrined in my software is those two things, if you can get the hydrogen spectrum, whatever you're looking for, it lends credibility to the model. If you can't get them, then you say, well, why not? Because what I'm saying is that there's nothing else. There's only these one-state quanta in this spatial model, and this is the system state of the universe. It's called the bit function, and these are the time development laws, and they are complete. There is no additional force. In the physics literature, every few months, someone comes out, oh, we saw something, there must be a fifth force or a sixth force, or whichever the count happens to be. But that's based upon particle interaction theories, which are have limited scientific merit at best. And my definition of fundamental forces in physics is based upon definite mathematical definitions, or clear mathematical and simple mathematical definitions. So that's the way we roll in science, okay?
Well, I'm not really sure I'm satisfied with your explanation of pair production, because like I said, that was basically just restating the obvious. I mean, I could have a theory that the world is made out of calculators.
Obvious that my spatial model and my
well, you're restating the obvious experimental result.
That's news to me.
No, what you're stating is the obvious experimental result. Like, how does pair production work? I could have a theory that says that the world is made out of calculators. And how does pair production work? It means that whenever the energy comes in, it just splits the calculators apart. And that's not, I mean, that's consistent. I mean, this is the problem with consistency.
Who's going to believe you?
And that's the problem, is that why should I believe you? Because your theory suffers from exactly that same problem. I mean, as ridiculous as it may seem to make the world out of calculators, it's just as plausible that your bit operators exist. It's kind of, replace
No, it's not.
your.
That's a false statement that you just made. It's not just as probable. If you don't believe in probabilities in physics, I think you're in the wrong chat. Okay.
Well,
It is
okay, I'll
not
give you
just
that.
as
Maybe that was a little extreme, but I mean, I would say
it's completely extreme.
well, I would say that this is
That's not the
probably.
way science rolls.
Well, I
Science
would.
rolls by a theory producing predictions which are found to be accurate.
And so I challenge you on, can you predict the, say, pair production, or can you predict the effects of the Lamb shift, or can you predict the spectra that comes out of at least hydrogen, or can you do something further, like can you do something which not even mainstream physics can do, say, predict a spectra that comes out of carbon? Now that's something
the only
that
problem there is the word "you." You're
Yes.
expecting me to do every experiment that you might want to think up.
Well,
I
not
have
every experiment, but
provided you
those are very
with a simulation
significant
program.
experiments.
I provided you with a simulation program based upon the model of space, the time development laws, and each of these things you can do. Okay?
But it's your theory that
When
I
you look
don't
at CERN,
believe.
they talking
Why
about
should I do an
the Atlas project. They have 1,000 physicists,
the problem
and
is
you're
that
asking me, just one little guy. What
yes,
about?
I am asking you, one little guy. It's your theory. The burden of proof is on you. See, the thing is that you have to have sufficient.
Well,
if
I've
you
got
want
about
help,
100 papers published already in the Journal of Binary Mechanics.
yes, and none of them seem to address this central problem of spectral generation. Now, it may be that your theory exists at a level where that's
Well, heck, they all
actually may
do.
not even be relevant. It may be, as John Erickson says, it's an emergent phenomenon. See, that's what Eric says. That's the generation of spectra may be an emergent phenomenon. I think your theory is more dealing with the actual emergence of, say, the electron and the positron itself. So, presuming that that's where that theory lies, then it may be that maybe that should be your answer, in that maybe your theory doesn't address that directly. But once you have an electron and a positron, blah blah blah, then the rest of these things could emerge out of that. At least that's the way it works in my theory. So in my theory, I don't have necessarily an explanation for what the heck an electron is, right? So I don't have anything like yours. But once you establish the existence of the electron, the positron, and quantized space, then you can get things like the spectra pretty easily, I think.
Well, show us.
Well, it's easy. I mean, let me show you how simple it is to get the spectra of hydrogen. All right, it's very simple. You don't need any math or anything. Okay, so this is, say, the proton. Okay, the red block is the proton, right? And then the black block is the electron. Okay, now normally ground state, they are in fact together, right? So normally this is hydrogen. Now when you generate spectra, it means you put energy in the system, which means that the electron becomes separated from the proton.
The electron and the positron are now hydrogen.
No, this is a proton. Okay, this is not a positron anymore.
You've turned everybody off right then.
This is a proton. Okay, we're just talking about protons before, because I don't have different blocks. So understand, this is a proton. This is an electron. This is not a positron. Okay, definitely not a positron. This is a proton. So we got free proton. This would be a hydrogen ion. This is an electron. Okay, so all you need to understand is that when you energize this thing, it rips the electron away from the proton, right? Now, the thing is that because space is quantized, it cannot take any arbitrary distance away from the proton. If space is quantized, then it has to be either here, or it has to be one other unit distance away, or here, or here, or here. It can only take quantized steps away from the proton.
Well, let's see the numbers. Let's see the numbers.
Right? Now the numbers are very simple. The numbers are the force between the electron and the proton is the Coulomb law, which is 1/2 over r squared. So that means that distance-wise and potential-wise, this is like 2 over r squared, 3 over r squared, 4 over r squared. So that's the only energy levels it can take. So when you have an electron and it's like out here at 3r, and then it comes slamming back here back onto the proton, the amount of potential, the amount of energy it can release is equal to the amount of the Coulomb force that are between the 2 points here. So if it slams straight down to the bottom, it's going to be 1 over 3 over r squared, or actually 1 over r3 to the squared is what it's going to be. It's just Coulomb force, right? 1 over r squared is Coulomb force. So, and if it doesn't come back like the whole way, like it goes from like 3 to 2, then the energy difference is just going to be the difference between the Coulomb force between those 2 spots, right? And this is actually Balmer's formula. That's why Balmer's formula looks exactly, it has the same form as Coulomb's law, which is 1 over r squared minus 1 over r squared, because it's just the electron taking quantized jumps away from the electron in order to produce that formula. And I mean, that's it. That's it. I don't need to do any fancy, and I could explain it in 5 minutes. It's just a difference in Coulomb force. The only thing you have to accept is that the electron can only move quantized distances away from the electron as it's being bounced around when it's being energized. And that's why we see quantization in the spectra, because the space is quantized, is why we get that quantization in the spectra.
Well,
So
you've gone one step. There's 2 other things you have to quantize, which is energy and time. So
yes, time is also quantized.
That's good. That's
time also has to be quantized. I mean, I think we agree on that. Space has to be quantized. You know, particles cannot occupy arbitrary locations in space. We agree on that, and we also agree that particles cannot move arbitrarily either. They have to move within a quantization of time. Both of those concepts are quite important. I think we share that, but from a physical model, my point is that my model, I can easily explain how that quantization happens. I don't have to point to a simulation. I don't have to point to a blackboard full of equations. All I have to do is point to is the Coulomb's law. That's it. That's all you need to do to figure this out. So I would say that that's one of the things that we like about theories. Like we call that beauty, or simplicity. That a theory which can be more easily explained, we tend to like better. So, like I said, I have a theory. All I need to explain the helium spectra is space quantization and time quantization. That's it, and Coulomb's law. Those 3 things will get you exactly the observed spectra. So that's why I like physical models. Now, with all due respect to James, like I said, I think that from what I've seen of your theory, that maybe your theory just doesn't directly address those issues, because once you get to the point where you would agree with me that, say, space is quantized and there are things called electrons and protons, then other theory can take over to explain the other observed phenomenon, like spectra. It may not be something that your theory even addresses, rather than saying that, well, just go look at the simulations and see what it spits out. I'm not sure that your simulations, actually even address this particular physical situation. Maybe it does. I don't know. Maybe it doesn't.
Well,
but
if they don't, I would like to see someone point out where they don't.
Like I said, you have to match. You have to match precisely what I just did, which is to show the physical basis behind why the quantization occurs. And if you could do that, great. But it doesn't sound like you have. So that's a hole in your theory, a hole big enough to drive a truck through.
Be my guest.
So no, this is not. I don't believe your theory. So, like I said, there's no point in me trying to prove your theory. It's your theory, I mean, I will vigorously defend my own theories, and that's my burden of proof. I would not, although I do have to, and you also too have to convince. You want somebody to help you, then you also have to convince them enough to help them. But it does sound like John, Eric, and Scott here. He sounds like he'll help you out there, and certainly I think you've got. As a alternative scientist, I certainly think you've got enough there to start. No one can complain. No one can complain about that. So, and you've got like hard computer simulations, and that's great. So, but I'm not sure. I'm just trying to figure out, where things fit, right?
James, I have a question. I have a simple question for you. You use the term spatial a lot as opposed to spatial. What is spatial?
Oh, okay, I guess that's my pronunciation, my mispronunciation of spatial. Of spatial.
Okay.
And I think someone thought you said spiritual.
Yeah, well, that was a real mishearing, but spatial, yeah, I'm completely familiar with, but spatial, which you're swapping the positions of the T and the I when you say it that way, was confusing me.
So the correct pronunciation is, sir?
Spatial.
Spatial. Okay.
All right.
Not
That's
spatial,
it. Thank
spatial.
you.
Okay, let's get that cleared up. It's tomato. Right, okay. It's okay. But let's see. Let's see here. Another interesting thing would be now this. It goes along the road of, okay, what experiments do you have to justify, say, your model, right? So one thing I wanted to try and point out is, say, in atomic physics, right? One problem in atomic physics is that you've got, two protons, and the question is, how is it they stay together in the atom? So mainstream says that there's this mysterious thing called the strong force, which holds these things together. And
yes.
I think that's a pile of bull. So the question is, if we reject that, then what would work, right? Now, I think what would work possibly is if you stuck like an electron between them, right? So if you stuck an electron between two protons, I've done this in simulation, this will stick together, right? So that's okay, right? But I don't think that the problem is this: if this was a proton, well, let's see here. No, I think that'd be okay. So it'd still end up with like +1, I guess. But okay. It's not that conducive to making very long chains. I mean, I don't think we think an atom is like this gigantic chain of positive, negative, as you can imagine, right? We don't think that atoms are straight, right? So I think the other way we could glue protons together is if we just put like two electrons between them. Then we get something that's a little bit more spherical, I would say, right? And I think, this is supported by what Bill Lucas says, which is that within the atom, the only forces that appear to be present are electrostatic Coulomb forces, right? And so that's just one way of doing that, which is to glue them together with opposite charges, right? So let's see, where was I going with? So I was going with this because this still isn't quite, say, helium, right? Because we got two protons, and that's fine. We got two neutrons, but generally speaking, there's these things called neutrons, which generally seem to need to be present, right? So why do we need? Why are they there? And I think that they are probably one of the gluing components. I mean, we've got the electrons here, but it does leave us with the question of where's everything else, I suppose. Now, I have a little bit more complicated theory on that, but the thing is that I'm thinking, and this is a little bit. This is not exactly what I'm what I'm proposing. But in order to, say, balance out this electron that we're using to glue on the glue the protons like that, you actually need another charge. So to balance out this electron. But I'm saying that this charge is actually going to be a positron, not a proton, right? So you've got the negative charge here. If you need something to balance it out, you need a positive charge. So what I've done is that, I've taken this unit, which is just positron electron, and I represented it by this white set of blocks here, right? So that's basically what I'm proposing the neutron is. The neutron is there. It's helping to glue the two protons together and still keep things neutral. So, this is just a physical model. So I'm proposing that what you really have here is two neutrons and two protons, but now we're kind of missing the electrons, right? Because if these electrons are bound into the system, helping to glue together the protons, and I think there's a kind of special bonding. There can be, like in chemistry, two kinds of bonds. One is like kind of a loose bond, and then there's a very tight bond. That the electron is doing a very tight bond to the proton, because you can put a lot of energy into an atom. You cannot break apart the protons, right? But what you do have is that since we've got these two spare positive charges, we can throw in, a loose electron right there, right? Okay, these are not very strongly bound onto the atom, I don't think, which is why they can be ionized off the atom fairly easily, right? So you can take this electron. It's not strongly bound. The strongly bound components would be the neutrons and the electrons and the protons to the electrons. Those are strongly bound. The electron probably kind of loosely bound. So that would explain why the electron can be easily ionized versus we cannot ionize off proton. The proton is stuck in there. It cannot be ionized, but the electron can be ionized because it's relatively loose, because it doesn't have a strong binding with everything else. And so this is what I think would be the helium.
Yeah.
The helium atom, I would think. So, and it's a perfectly spherical, and it's perfectly symmetric, and all the charges are completely satisfied, in meaning that there's no asymmetrical thing. Like if there's some asymmetrical thing like this hanging out there, then you would have an asymmetric force, and something would try and bind to that. But in helium, it would be a perfect cube. So, but that's kind of how I explain a couple of the fundamental aspects of atomic
He's
theory,
talking about his theory.
which is, why the neutrons are there. Why can you put so many on? Because you can't stick arbitrary numbers of neutrons on. And I find that, there are certain rules that can be applied, that you can apply neutrons to only certain places. Like you can't apply a neutron to a neutron, but certainly these spots that have the proton electron can take another neutron. So you can add on a few more neutrons into helium. Possibly you could stick one here, stick one there. They can't really stick onto each other. But using rules like that, I've explored that and going, yeah, it roughly works out that there's only so many spots you could add another electron onto your atom there, right? But that's just an explanation, like James says, what experimental evidence do you have for your model? And this explains a lot of things that the mainstream model doesn't explain. Like it's kind of curious that we think that the protons are glued together by the strong force, but have absolutely no explanation for why the neutrons are present, right? But this physical model does explain why the neutrons do need to be present. So I think that's a fairly significant gain or advantage to doing something like that.
So what is the proton? At first,
well, actually, what I think the proton is, if you were to compose it of individual of individual positrons, electrons, then the proton would really be something like this, or maybe something like this. Or it does contain 3 components, and I think experimentally we do see that the proton contains 3 components, and it does have the correct charge, which is net +1. So, but I'm not sure about this linear shape. I think energy-wise, it does need to be a linear shape like this. But within an atom itself, it does still need another electron to glue it together with its neighboring proton, and it doesn't look very pretty in a linear fashion. In my other papers, it may be a triangular kind of thing there. So maybe the electron that glues together the proton goes, somewhere else, like here or something, So it's more an even thing. But a proton is just 2 positrons and electrons. So that's the way it works in my theory. And in my theory, like I said, I made my big rant against why quarks don't exist. And I think that part of the reason for that is that I think they don't need to exist. That this whole fractional thing was actually motivated onto trying to make a neutron have 3 pieces, right? A neutron in conventional mainstream physics needs to have 3 pieces, but in all my research, I cannot find any equivalent experiment to the proton to show that this thing actually contains 3 pieces. Me personally, I think in my theory, the neutron only contains 2 pieces, positron and an electron. So when we see free neutrons, I told you that space itself is made out of positron electrons. And so the neutron and this piece of thing that space is made out of would actually be physically identically the same thing. So if you're looking for what the ether particle is, I would say space is actually filled with, say, neutrons, if that's the easiest way for you to understand it. The only difference between the neutrons that we see and the neutrons that make up space is that the neutrons that we see are in motion. They have motion against the background. And one of my interesting predictions experimentally is that if you slowed down a neutron enough, it would just simply disappear, right? It would just meld back into the unidentifiable sea of neutrons that are out there in space. And I think we do see that. We see neutron anomalies, and we see, neutrons that do seem to behave this way. They just unaccounted, a certain amount of them just disappear, right? But you could do a direct experiment, say, if we take these neutrons and we slow them down to 0, I would predict they would in fact disappear, and they wouldn't decay. You wouldn't see any decay. They would in fact just completely disappear.
So you don't believe in conservation of energy?
No, I believe energy is absolutely. Where does energy not conserve there?
Well, if they disappear, something must be somewhere.
Yes, they just disappear as if you put a drop of water in a cup of water.
That's magician talk.
No, that's
Science
not.
talk is where you say we have one composition of quanta, which goes into another, that quanta are neither destroyed or created, the one-state bits. That's conservation of energy. So just disappear, that's for vaudeville magic shows.
Yeah, nothing disappears.
Not science.
I would say it only disappears in the sense that we can't see it, but it's definitely there. There's, I believe, an absolute conservation of matter and energy. Anytime you see something that looks like it disappears, it's actually just melded back into the background. It's just like if you were a scientist and you were looking at hydrogen and oxygen while you're in a cup of water, and you reacted the hydrogen and oxygen together, and what does it do? It creates another water molecule. But from an experimental standpoint, you think it just disappeared, right? Because you can't see the hydrogen and the oxygen anymore. You can't see anything different than the background. And that would be the difference. So it's not actually, nothing ever actually disappears, if that's what we were thinking about conservation of matter and energy. And this has always been a bugaboo with me about because they say that, you know, you convert energy into matter and matter into energy. And I'm saying that that conversion does not allow you to break the laws of conservation for matter and energy. I think somebody just wrote like a 2-sentence paper disproving relativity because it's a violation of the conservation of mass. And it's like, duh, yeah, that's a if you can take two particles and make them disappear, as we think annihilation does with the positron electron, you know, they think the positron electron come together, they disappear, they completely convert into gamma rays, and the original positron electron do not exist, right? And I think that that is a violation.
So what are gamma rays made of?
Well, gamma rays are what we think they are, which is they're electromagnetic waves, just at a very high frequency. That's all it
doesn't
is.
say what they're made of.
They're made out of waves, just like in a bathtub. If I put my hand up and down,
What is a
or
wave?
a wave is a
I mean-
compression and rarefication of a medium, just like air. So I think we know precisely what's going on with air and sound waves. So but you do need to have some sort of medium that's compressible. And once you have that, then you can create regions of higher density, regions of lower density, and there has to be some elasticity in the system. But as soon as you have that, then you can do the same mechanism that we have through air, which is a compression rarefication of the medium. And that's exactly what a wave is. And so Cornelius here, you know, he has this this thing about the strong, tight bound and loosely bound. And like I said, I would say that that is a little loosey-goosey, but we do have concepts of like that in chemistry, right? So it's not like I'm pulling that one out of the air, right? Certainly in chemistry, we have the concept of binding strength, and there's different binding strengths. And it's a matter of, we definitely observe those things. Not everything is bound together with the same amount of force. It depends on a matter of geometry to how strong those bonds will be. But I only use that just to explain why is it we can ionize off the electrons, but we cannot ionize off the protons, right? You can try as hard as you want. And if you did ionize off the protons, then you'd be doing alchemy, right? You'd be converting. And I guess technically you can do that. If you smash two things together at high enough rates, you can break apart proton bonds. But generally speaking, not so much.
Well, in my work, above the plasma range, is where the ionization energy levels occur that you just spoke of, Franklin. You have the lepton quark range, which elsewhere is called the quark-gluon range, and our quark-gluon soup. I call it the lepton quark soup because actually leptons predominate, and that's up to about 0.75 and above maximum energy density. So in that range, you have almost pure energy. And by the way, when you're getting up to the so-called speed of light in accelerated proton beams, the people, like for example at CERN, don't seem to know what they're talking about. They don't actually have proton beams as commonly understood. They have lepton quark or beams, and yet they're calling them proton beams, which almost borders on fraud, actually, concerning the some 20 million or more dollars of funding that at least U.S. researchers are getting per year for the certain groups of CME or CMS, excuse me, and ALICE.
Well, everyone's got to make a living, I suppose. I see Jonathan Erickson Scott. He's made a comment here. Now, I'm kind of rabid on this point, so I'll have to say that this particular view that waves give rise to particles, I would say that I am extremely violently opposed to this idea that waves give rise to particles. Now, that's primarily because if you have waves, that already, like I explained, presumes you have a medium made out of particles, right? And then you have to go, well, then what are those particles made of? Oh, those made of other waves. And are those other waves made of more particles? So that's completely circular in my opinion. I reject it outright. I would think that the only way you can solve that problem is if you accept particles as fundamental. Once you have particles, then you can have waves. That is clearly the hierarchy for how particles and waves are arranged. You do not say that waves make particles, all right? That's my opinion, but I think that's a fairly good argument against that. So, and let's see, I want to respond to this other comment by Cornelius. It was your claim that the strong force did not exist. Yes, the strong force as a force which glues together bare protons does not exist. What I'm saying is that there's a force, the Coulomb force, which glues together the atoms, and that force can vary. There can be stronger forces and there can be weaker forces. I mean, basically, you think once a positron is attached directly to a neutron, that nothing else would really be able to attach to it. But that's apparently not the case. You can get apparently one more thing attached onto this. And once you do that, then there's really not that much attraction force left. And it's all based on the Coulomb force, not any other weak force, not any strong force. And that's how the hierarchy works. If there is no strong force, there's nothing that glues together bare protons. That would be my claim. So let's
I
see
have a
here.
suggestion. I have a suggestion that when people bring up questions like from the YouTube group that you're showing on the screen and so forth, that you actually poll as moderator. You poll all of the participants one by one. What is your response to that? Because right now we have only your response. And to be more fair and balanced, you might poll and then you yourself take the last shot and give each one of the participants an opportunity to respond first to each topic that is raised. Just a suggestion that might
Yeah,
make
we could do that.
the chats, in other words, that you play more a role of as a moderator rather than a role of this is my theory role.
Yep. Although that will definitely, there's certain times when I'm explaining my theory, like I did today, and that's fine. And there'll be different times.
Franklin, you're doing a great job. I have nothing but praise for what you're doing. It's just a little suggestion to make things more balanced. Because if every point that someone raises, you're the only one that responds, well, what are the rest of us even doing here then?
Well, I always allow you to interrupt. That's why I keep you. If you're in the live room,
I think
you can speak anytime.
Should moderate.
No, not exactly. I guess I would have to disagree. I would have to disagree that this is a science chat. It's like we were in a coffee shop, right? It is not a presidential debate, although presidential debates have been getting pretty out of control anyways. But it's like at a coffee shop. And if you have a contrasting argument, then because you are in the live room, then I invite you to comment immediately. So,
well, you see, like for example, I probably got more time in today's chat than some of the other participants. A moderator, in my conception, and again, I could be entirely wrong. Maybe everyone's very, very happy, but I would rather say, Keen has said this, or Jonathan Scott through YouTube has made this comment. Okay, Ian, what do you think? Cliff, what do you think? Alistair, what do you think? No comment? Okay, fine. Let's go to the next person. And so that basically the amount of talking time that each participant has is roughly equal. Right now, and again, it's a natural thing to do. You're sort of responding to everything. And, well, I mean, is it like the Franklin show, or is it Franklin as a moderator? You would still
get the Franklin
show. Okay.
It's my show.
I've suggested in the past that it would be advantageous if one specifically asked all the participants what their views were. I think the late Glenn Baxter used to do this. He would always ask for a contribution from each member and then indeed a summary from each member before the end of the conference. The reason for that is that whilst not all people will be as interested in a particular topic as some others will, some are more reluctant to speak actually and to make a point and to interrupt, and they're not as voluble, they're not as talkative. So it would be an advantage if maybe on top of giving his own view, the moderator did twist the arm a little of all the speakers to get their views.
Yes,
Yes,
part
and
of
I
the
thank
reason.
you, Ian, for jumping in, especially when I have to, go out and help my
Yeah.
mom, and she's calling again. She's going, "It's 9 o'clock. You're supposed to help me." So,
You're
Part of the
continuing. I thought it was near the end of it, Franklin. Are you continuing?
no, actually, I think we've run out of time and my mom is calling me. So I'm gonna have to say thank you for everyone participating today, and we'll have to do this next week. All right.
Bye-bye.
Right.
And okay, let's go out.